Last time, again, we're in chapter 10, and we're talking about solutions, and we talked about some concentration units again, and a couple that are sort of important for what we talked about towards the end there. We have obviously our molarity, but also our molality, which is our moles of our solute over kilograms of solvent. We also have our mole fraction, which is in several or a couple of the colligative type properties, which once again is the moles of what you're interested in over the total moles. And really that led us into our colligative properties of solutions. They really do depend on the amount of solute present, and really more so the number of particles that are present in the actual solution. So remember that, as we talked about last time, if you have, say, a solvent by itself, just say like water or something of that nature, you know, there's with nothing in there, you know, there's nothing really to sort of prevent it from being able to sort of do its natural process of escaping from the surface of the liquid and go into the gas phase. As say we're talking about evaporation that's going on. Same thing as well in the freezing sort of aspect of it. If it's just really solvent molecules there, they're going to be able to interact with each other with really nothing getting in the way. It's when we do add some type of solute, some type of particles to the solution, that we do get a situation where we got these other guys sort of in there. And it takes a little bit more effort, if you will, for those solvent molecules to sort of escape. Also takes a little bit more effort as well for them to sort of come together as they are freezing. And it has an effect on several sort of aspects of a solution, including vapor pressure was one of them that we talked about. And what happens with vapor pressure is it is actually lowered. So we have vapor pressure lowering as a result of this sort of interaction. And we have a formula where it is the pressure of the component there times the pressure of the solvent by itself. So this is sort of the pressure of the solution. This is the mole fraction of the component of the solution there. And that is the pressure of the solvent is normal sort of vapor pressure in this particular case. Now it's vapor pressure lowering because of these guys sort of getting in the way. That means really only lower amount of gas molecules will sort of escape the surface. And remember, vapor pressure is basically the pressure of the gas molecules above the liquid who's been able to basically escape it through evaporation and stuff like that. So if it takes longer and it's a little bit harder for those guys to escape into the gas phase, then obviously we would have less gas molecules above the liquid. Less gas molecules above the liquid would mean obviously we have less pressure above the liquid, and that is why we see the vapor pressure come down. It also has an effect on things that we talked about, like freezing point depression. And boiling point, it actually will increase it. So boiling point elevation is sometimes called. And they have very similar formulas for a freezing point. The change in the freezing point temperature is equal to Kf times the molality. And for boiling point, it is the change in the boiling point temperature is equal to Kb times the molality. Here for these guys, a couple important things that we talked about. First off, Kf and Kb, those are constants. And they are based on the actual solvent, so not the solution. So when you go to the Kb or Kf table, you will find basically solvents listed there. So you might not find obviously the solution you're dealing with. Again, in a lot of cases, water is a very common solvent, obviously, as we talked about. But also, as we mentioned, again, not always going to be the solvent. So you want to make sure you pick out the right solvent. Along with that, you also want to make sure you pick out the correct sort of normal boiling point and freezing point for the solvent. Once again, if it is water, it's 0 degrees Celsius and 100 degrees Celsius for boiling point. But once again, if it is not water, just solvent, you need to find the correct boiling and freezing point for that particular solvent. A lot of times they are on the same sort of table as these guys. The other important thing to remember is to get you to either sort of add or subtract correctly and end up with the right sign. Remember that this is not the freezing point temperature, but it is actually the change in freezing point temperature. And because the freezing point temperature is depressed, that means the solution will actually freeze at a lower temperature than the solvent. It is defined as the temperature of the pure solvent minus the temperature of the solution. And if you do it that way, that will get you sort of the correct sign. So like an example we did yesterday, I think, if you found the change of freezing point was 3 degrees Celsius and 0 degrees Celsius was your normal freezing point, that would mean the temperature of the solution when you distribute that negative sort of to the other side would give you a negative 3 degrees Celsius, which is it coming down rather than just 3 degrees Celsius if you kind of did it the wrong way. So this is really important to remember. It gets you sort of the correct sign, adding and subtracting correctly. And it's a little different for boiling point elevation because the boiling point of the solution is actually larger or goes up. It is higher than that of the pure solvent. The change in boiling point temperature is actually the temperature of the solution minus the temperature of the solvent. This once again will also give you sort of the correct sort of way of getting to the answer. So once again, here, if we did a made up example of 3 degrees Celsius being our change in boiling point temperature, our solution is what we're looking for, and say it was water, which was 100 degrees Celsius, we would add that 100 to the other side and get us 103 degrees Celsius, which would be, again, an increase in the boiling point. So those two things are actually fairly important in addition to the formulas, to understand sort of how to manipulate those final answers so that you get it. And also remember that we saw here that we could use things like freezing point and boiling point to solve for other things like molar mass. And we could do that by using the molality and the change of freezing point and boiling point temperatures to figure out the moles. And then if you have the grams, you could get the molar mass from that, 3 grams per mole. Any questions on any of that stuff there that we talked about last time? Okay, we did an example, I think, a boiling point and stuff at the end. So I think we're here at osmotic pressure. Osmotic pressure is when a solution is separated from its solvent by a semi-pyramidal membrane. The solvent molecules will pass through the membrane. So if you have sort of a situation, for example, got like a tube or something like this. You got like a membrane here on one side. And say on one side you have something like salt water. And on the other side you have just pure water. The process of osmosis, as we'll talk about here in a little bit as well, the process of osmosis is the process where solvent molecules will move from a lower concentration to a high. Take a look here. We'll go third time a charm here. Hopefully the internet works here. All right. So we're looking for the molar mass. So we are looking for grams per mole. And we do have 5.87 milligrams given to us, which is not exactly grams, but that will get us to grams in terms of molar mass. So we definitely could use that for the molar mass. Then we have basically a volume that is 10 milliliters. We got a pressure that is 2.45 torr, and we got a temperature that's 25 degrees Celsius. So once again, this is osmotic pressure, and again, it is this formula here, T over V, but really, it is exactly the same as PV is equal to nRT. So if we think about what we have temperature, we have volume, we have pressure, we always have R. We don't have moles here, and that is actually what we do need here to kind of solve for the molar mass. So we're really going to use the osmotic pressure equation, or really the ideal gas law here, to figure out moles, and that will allow us to get to the molar mass. Pretty much identical to how we calculated the molar mass of a gas when we were doing the gas sort of calculations. So here we're going to solve for N. N would be PV over RT. It is important, although, it may be disguised here, it is still really the ideal gas law. So you still need to make sure everybody's in the correct units. So we do need to convert our volume into liters. So if we divide that by 1,000, that gives us 0.01 liters. We also need to convert our pressure into atmospheres. So we're going to divide by the 760 to do that, to get it into the correct units. And if we do that there, we will get 2.45 divided by 760 gives us 0.00322 go 6 atmospheres. And obviously, like anything else involving temperature, going to convert that guy to Kelvin. So we're going to add our 273 to it. So now we have everything, I think, in the correct units. Our volume, our gas constant, which we always have, and our temperature at 298. Everything should cancel out here except for moles. And we will end up with here divided by 0.026 and 298 there. That will look like 1.32 times 10 to the -6 moles. So that is obviously the mole part of the molar mass. The grams part, we also do need to do a conversion. So we have 5.87 milligrams dividing by 1,000 milligrams in a gram. Basically, we'll move over a decimal place there. Gives us 0.00587 grams. We now have grams. We now have moles. So the molar mass here would be our grams divided by our moles. And we end up with here. Looks like 4.7 grams per mole, or maybe like a 4.450 grams per mole. Any questions on that? So pretty much identical. The good news is osmotic pressure pretty much identical to the ideal gas law, and obviously that application like we did molar mass earlier. Any questions on that one there? All right, so why don't we try another one here? The molar mass of a lysozyme is 0.0. What is the molar mass of a lysozyme? Well, that is 0.075 grams per 100 milliliters, and gives an osmotic pressure of 1.32 times 10 to minus 3 atmospheres at 25 degrees Celsius. Okay, let's take a look at this one here. So once again, we're looking for molar mass for like the previous example there. So we want both of those things, grams per mole. So once again, we can see in the problem here, we do have actually the grams to go. So that's good to go. The rest again is going to be our sort of gas law information for our osmotic pressure. So we have a volume there that is 100 milliliters. We got our pressure, which is 1.32 times 10 to minus 3 atmospheres. We got our temperature, that is 25 degrees Celsius. So once again here, we could do our PV is equal to nRT. We're going to use it to solve for moles. Once again, a little conversion here. We're going to convert this to liters. So that's going to be 0.1 liters. Atmospheres is good. So we'll add our 273 over here, and that gets us our 298 Kelvin. And now we can solve for N, take an RT to the other side, gives us PV over RT. And that gets us our 1.32 times 10 to minus 3 atmospheres, our 0.1 liters divided by our R. And our 298 Kelvin. Again, everything is going to cancel except for moles, which is good. And that gets us for moles here. About 5.40 times 10 to the minus 6, I believe. So to our molar mass now, since our grams are already in grams, so that's good, 0.075 grams and 5.4 times 10 to minus 6 moles. Looks like it gets us a 13.894 grams per mole. And maybe clean it up a little bit there. We'll call it 13.9, why not, grams per mole. Any questions on osmotic pressure calculations? Like I said, the good news is it's pretty much the ideal gas law. So we've done that one before. And again, here using it to solve for something like molar mass, you obviously can use it just to solve directly for osmotic pressure as well, by just putting the numbers into the ideal gas law. Any questions on that there? All right, so the next thing we're going to talk about is basically these colligative properties and what happens when we actually dissolve something in a solvent that is maybe ionic. And that brings up what is sometimes referred to as the von Hoff factors that you do need to take into account for our formulas here. I can find it right here. So, for example, up to this point, all of these sort of solutes that we have done has been really non-ionic. They're kind of been molecular. They've been carbons, hydrogens, oxygens, and that means that when those something like that, sugar goes in, it stays as sugar basically on the other side. It's basically a one-to-one relationship of what you get. Because colligative properties are based on the number of particles that are present, and it has an effect obviously on things like boiling point, freezing point, vapor pressure that we talked about. The number of particles that you get when you dissolve something in there is really important. When we take a solute that is ionic, different things happen. So for example, if we dissolve something like sodium chloride in water, we would get the presence of sodium ions floating around, and we would get the presence of chloride ions basically floating around. So for every one of these sort of sodium chloride units that we toss in there, we actually will produce 1 and 1, which is 2 total particles that are basically produced in this case. You know, if you had something like calcium chloride, same idea. You would take calcium plus a couple chlorides here, and that would give you basically 3 particles that are floating around. So the von Hoff factor is basically an adjustment that is made to these sort of these colligative properties to account for the greater number of particles that we see in a actual solution, especially if the sort of solute is ionic. Now, if the solute is non-ionic, like a lot of the examples that we did up to this point, basically the factor is 1, so we don't have to worry about it. The von Hoff factor is basically abbreviated with an I to stand for it. So in this situation of what we looked at here, if it was sort of a non-ionic solute, the I would equal 1, which is why we really don't take it into account in this case, or previously. If we look at something like sodium chloride, the I factor now becomes 2. And if we look at something like calcium chloride, the I factor now is 3, or the von Hoff factor there is 3. And that does affect all of those sort of colligative properties that we just talked about. You basically can take all of those sort of formulas, like the change in the freezing point temperature would be I times Kf times M, and insert that von Hoff factor there. If you took the change in freezing point, boiling point temperature, Kb, it would be I times all right, try that again. It would be I times the Kb times the molality. If you did our little osmotic pressure that we just did there, you could also incorporate the I there. You could also incorporate the I into the vapor pressure lowering that we saw previously. I will say that this one is a little bit different, the way that you handle sort of vapor pressure lowering. Typically with the I, we incorporate it into actually the mole fraction part of it. So we do incorporate that into the mole fraction part of it. And remember that the mole fraction here is the moles of what we're interested in, divided by obviously the total moles in this case. So the total moles would pretty much be the moles of the solute plus the moles of the solvent. And where we would incorporate I is really into here in the moles of the solute here. So for example, let's just say that our salt was sodium chloride. And let's just say we had, 0.12 moles of it. When we would go to calculate our mole fraction, we would basically do this move, 0.12 moles of sodium chloride. For every 1 mole of sodium chloride, you get basically 2 moles of particles that would happen. And we would want to use in our mole fraction 0.24 moles there for our solute, because it has basically twice the amount of particles that are floating around. So you get twice the moles of each of those ions that are present. So when you're doing sort of Raoult's law, which is this vapor pressure lowering here, that is sort of where we incorporate I most of the time, is sort of into those moles of the solute there. And by doing basically timesing the moles of the solute by, if there's 2 ions, 2, if it's 3 is 3, and so forth. Most of the other ones, you basically just kind of lock your sort of I value into there, like it is 2, 3, whatever it may be. So, for example, how would it differ? How would the change in temperature differ if we had, sodium chloride dissolved in, say, water versus, say, a sugar or glucose, or dissolved in sort of water, if you will. So let's just say, for example, the molality in each case was 4 molal, and obviously Kf here would be 1.86 degrees Celsius times molality. So if we did it for glucose, where basically I would equal 1, since it's molecular and not going to break up into ions, we would get, obviously, in this case, our change in freezing point temperature would be basically 1.86 times 4 would give us a change in temperature of 4 times 1.86. Whoops, 1.86 times 4. About 7.44 degrees Celsius. If we did this same calculation, though, with the same values, but it was sodium chloride that would put in there, that I would equal 2. And we would end up with 2 times 1.86 degrees Celsius and our 4. And once again, here we would end up with a change in temperature of about 14.88 degrees Celsius. So you can see that by putting the sodium chloride in there, because it breaks apart into twice as much in terms of the ions and particles are present, it has a greater effect, obviously, on the freezing point because of the presence of more particles in that solution. Kind of like some rock salt and some water, right, and ice, and you make some homemade ice cream, right, and all that kind of stuff. It really lowers the freezing point down when you do that. So again, the only kind of weird one is, again, the incorporation of I a lot of times with the Raoult's law, and the vapor pressure does sort of occur in the mole fraction part of it. Any questions on that there? So if it's an ionic thing and you're doing anything like freezing points, boiling points, those things, you do have to take into account the number of ions that are present. What we'll do in most problems, and what you do in most problems, is you kind of do it based off of the formula. So based off of the formula, again, of something like sodium chloride, we do get our 2 ions, which means I is equal to 2. In reality, in most cases, experimentally, I is actually going to be probably less than that. And that is because when you get some ions together in solution, they are sort of attracted to each other. So what ends up happening is you get some ion-ion interaction that occurs, and they end up being one giant sort of unit, if you will, rather than free-floating sort of ions and stuff like that. And what that ends up doing is actually lowering the number of particles in there because they kind of group together a little bit, even in that sort of situation as they're surrounded by water. So in reality, if you were to experimentally sort of determine I, they typically will be a little bit lower than what we would predict from the formula. But in most sort of textbooks, you could just go based off of the formula and go, hey, it breaks into 3, so I is 3, or it breaks into 2 ions, I is 2, and so forth. But in reality, it will be a little bit lower than that. And that's what we see here in this picture. Even this sort of interaction that does start to occur between this, some ion pairing. And what that net does is just makes that one sort of big ion, if you will, and lowers the total number of particles. And that's why we see measured, they are slightly lower than what would be predicted by just the formula here of breaking them apart. But for our purposes here and most purposes, you could just go strictly by the formula to figure out your von Hoff factor. Any questions on that there? Okay, so why don't you do this one? What is the measured von Hoff factor if 0.05 molal calcium chloride has a freezing point of minus 0.27 degrees Celsius? The KF for water was 1.86. Okay, let's take a look here and see. So we're doing freezing point, so it's going to be the change in our freezing point temperature. And in this case, it is calcium chloride, which is ionic. So we would incorporate the von Hoff factor into it, which would be the I, our KF, and our molality. And in this particular case, we do have the freezing point temperature of minus 0.27 degrees. A reminder that that is actually the freezing point temperature, not the change of freezing point temperature, which would be the solvent minus the solution. So once again here, the change in our freezing point temperature would be 0 degrees Celsius minus a minus 0.27 degrees Celsius. That is how we get rid of the negative here. And it actually is 0.27 degrees Celsius, which would be our change in freezing point temperature. So that would give us 0.27 degrees Celsius is equal to I, which is what we're looking for, or 1.86 degrees Celsius times molality, and our molality, which was already calculated for us. Molalities cancel, Celsius will cancel. So we're going to divide that 1.86 and the 0.05 to the other side, and that gets us a value here of about an I value of 2.9. So this is the measured I value of 2.9, which if we just went straight off of the formula for calcium chloride here, it would break apart into 1 calcium and 2 chlorides. We would predict that the I value would be 3. So here again, you can see it's a little bit lower than what would be predicted by the formula, but you can go by the formula here. Any questions on that there? All right, so let's try one here just to kind of see here. Actually, let's see. What would be the boiling point temperature of a solution that is made by mixing 0.454 kilograms of sodium chloride and in 4 kilograms of water. So the KB for water here is 0.512, I believe. All right, so what is the boiling point temperature in degrees Celsius for a solution that is made by mixing 0.45 kilograms of sodium chloride in 4 kilograms of water? What is the boiling point temperature of a solution that is made by mixing 0.45 kilograms of sodium chloride in 4 kilograms of salt? KB there is 0.512. So I believe our change in our boiling point temperature here, we will incorporate the I here because this is sodium chloride, and our KB and our molality. In this case, we don't have the molality calculated. So we'll do that. So we'll convert our 0.454 kilograms of sodium chloride into grams. So 1 kilogram is 1,000 grams. That's going to give us 454 grams of sodium chloride. We'll divide that by the molar mass of sodium chloride, 5844. And that will get us 7.769 moles of sodium chloride. To turn that into our molality here, we're already in kilograms of our solvent. So 7.769 moles over our 4 kilograms of solvent. And that would get us a 1.94 molality. Any questions on that so far? Here we have the molality, we have the KB, which we obviously would find from a table. We will use the I value based off of the formula here. And obviously, as we've seen a number of times up to this point, that is going to give us an I value of 2 because it will break apart into 2 particles. That means the change in the boiling point temperature here would be 2 times our 0.512 degrees Celsius times molality, which is our KB value for water. Our 1.94 molality there cancels. That gives us a change in boiling point temperature of 1.94 times 0.512 times 2, about 1.99 degrees Celsius. A reminder that that is not the actual boiling point temperature. We do need to use our relationship that the temperature of the solution will be higher than the solvent in this case. That will give us a 1.99 degrees Celsius equal the temperature of the solution minus the normal boiling point of water, which is 100 degrees Celsius. That means we will end up with a whopping boiling point here of about 100 and we'll call it 2 degrees Celsius. First off, any questions on that calculation? So a lot of people, when they make pasta, right, they boil water, they throw some salt in it, to increase the boiling point and make it boil. This is basically putting a pound of salt into water. Yes, and you get a degree of that's about 4 quarts of water there. So that will raise the temperature about 2 degrees Celsius. So in reality, when you do your pinch of salt, you're probably not putting a pound of salt into your water, I'd imagine, and stuff like that. So, you're probably not raising the boiling point all that much. Just makes it taste probably a little bit better, maybe with the salt in the water and stuff like that. So in this case, you would have to throw in like a pound of salt to get that boiling point up. Any questions on that there? Okay. So why don't you see here? Why don't you try this one here? A solution contains 0.102 moles of calcium nitrate. You may not have this one, so you might have to write it down. A solution contains 0.102 moles of calcium nitrate and 0.927 moles of water. Calculate the vapor pressure of the solution. And the vapor pressure of water at 55 degrees is 118.14. Look at this one. So this is our vapor pressure lowering. So Raoult's law here. Again, we're going to incorporate the I into here because it is calcium nitrate, which is our solute. And this is our solvent in this case. Now, remember that really with Raoult's law here, the I actually gets kind of incorporated into the mole fraction part of it, and that's really where we're going to kind of incorporate that into. So we do want the mole fraction of water, And to do that, it would be the moles of the water over the total moles, which in this case would obviously be the moles of the water. We do also need to take into account really the moles of our solute here. But since our solute in this case is ionic, it will obviously generate more particles than a non-ionic one. So our calcium nitrate here, when it breaks apart, obviously will give us a calcium plus a couple of nitrates, which means really here we're going to get 3 sort of particles or I value there incorporated. So it is incorporated a little bit differently here. You could do sort of this relationship that we do have 0.102 moles of our solute. And for every 1 mole of that solute, we really will get 3 particles here, really. The 3 moles of particles that will happen. So we really need to kind of multiply that 0.12 by 3, because when it breaks apart, you're going to get basically a 3-to-1 sort of relationship for it. So 3 times 0.102, and that's really where we're going to incorporate the I into this problem. Again, on the other sort of colligative properties, you don't have to worry about it. It's really just this one here with the mole fraction that you have to do that. So that actually would be the proper moles of our solute in this case. Again, adjusting it for the factor of 3 because we're going to get 3 particles per. Now, when we do our mole fraction for water, we could do it correctly using the moles of the water, which is 0.927, divided by our corrected value here for our solute because it's ionic, plus our 0.927, and that would get us here. Does give us like 0.752. Now we could go into our Raoult's law and find that the vapor pressure of our solution will be 0.752. That already took into account really both of those things, the mole fraction and the I value was taken into account there, times the vapor pressure of just water at 55 degrees, which is 118.1 torr. And we end up here with, not that, try that, there we go, about 88.79 torr as our vapor pressure of the solution. And it should go down, as we talked about, again, with the presence of all these particles flying around. That's going to allow less of the water molecules to escape the surface. That means there'll be less water molecules above the surface of the liquid. Less gas molecules above the surface of the liquid means that there will be lower pressure than we would expect with the pure solvent by itself. And that's what we see here. Pure solvent by itself, vapor pressure 118, more water molecules could escape. With all those guys floating around, it drops significantly down to about 89-ish torr in terms of its vapor pressure. So it was lowered, like the vapor pressure lower than we would account for. So again, this little aspect here is sort of how we incorporate I in these Raoult's law problems versus vapor pressure lowering. It's again kind of incorporated into the mole fraction part. For everything else, like we saw before, the boiling point, the freezing point, and all that, it's just kind of put into the formula. You can do it, just times it and by it. But we do incorporate here into the mole fraction part. Any questions on that there? Okay, we will lay it up for now.